Statistics. The very word might make you think of endless columns of numbers or complicated graphs. But in reality, statistics is about understanding the stories hidden within data. It's about finding the signal in the noise. Statistics helps us make sense of the world around us, from predicting election outcomes to understanding the effectiveness of new medicines. In our daily lives, we encounter statistics everywhere. When you hear that the average height of women in a certain country is 5 feet 4 inches, you're dealing with statistics. When you read that a particular stock has an average return of 7% per year, that's statistics too. Statistics gives us the tools to collect, analyze, and interpret data, allowing us to draw meaningful conclusions and make informed decisions. Whether you're a student, a professional, or simply someone who wants to understand the world better, having a basic grasp of statistics is essential. Imagine you're comparing the heights of students in 2 different classrooms. You might think that if the average height is the same, the students must be quite similar. Class A has an average height of 5 feet 5 inches, and Class B also has an average height of 5 feet 5 inches. Does this mean the heights of students in both classes are identical? Not necessarily. The average height alone doesn't tell the whole story. This is where the concept of variability comes in. Variability helps us understand the differences within the data. Variability refers to how spread out or clustered together data points are. It gives us a sense of the range and distribution. 2 datasets can have the same average but very different levels of variability. This can significantly impact our interpretation. For example, Class A might have students ranging from 5 feet 3 inches to 5 feet 7 inches, while Class B might have students ranging from 5 feet to 6 feet. This wider range indicates more variability. Both classes have the same average height, but the heights in Class B are more spread out or variable. This spread can affect how we perceive the data. Understanding variability is crucial in statistics because it tells us how representative an average, like the mean, is of a dataset. It helps us gauge the reliability of our conclusions. A high variability means the data points are more spread out, and the average might not be a good representation of the typical value. This insight is essential for making informed decisions based on data. While several measures quantify variability, standard deviation is one of the most widely used and powerful. In simple terms, standard deviation tells us the average distance of individual data points from the mean of the data set. A low standard deviation means the data points are clustered closely around the mean, while a high standard deviation indicates that the data points are more spread out. Think of it like this. Imagine you're playing darts, and your target is the mean of a data set. The standard deviation represents the average distance your darts land from the bullseye. A smaller standard deviation means you're more accurate and your darts are closer to the target. Standard deviation provides valuable information about the distribution of data and is a key concept in many statistical analyses, including hypothesis testing, regression analysis, and more. The standard deviation formula might seem intimidating at first glance, but it's actually quite straightforward once you understand the individual components. Let's break it down step by step. First, calculate the mean or average of the dataset. This is denoted by the symbol X bar. Next, find the difference between each data point and the mean. This tells us how far each data point deviates from the average, then square each of these differences. This eliminates negative values and emphasizes larger deviations. After that, sum up all the squared differences. Then divide the sum by the number of data points minus 1. This gives us the variance, which represents the average squared deviation from the mean. Finally, take the square root of the variance. This gives us the standard deviation, which is in the same units as the original data. Section 5, a practical example. Calculating standard deviation. To solidify our understanding, let's walk through a practical example. This will help us see how the theoretical concepts we've discussed apply in a real-world scenario. Suppose we have the following dataset representing the number of hours 5 students spent studying for an exam. The values are 5, 7, 6, 8, and 4 hours. Step 1. Calculate the mean denoted as x, is calculated by adding all the values and dividing by the number of values. This gives us a central value around which the data points are distributed. So, 5 plus 7 plus 6 plus 8 plus 4 divided by 5 equals 6 hours. This is our mean study time. Step 2, calculate the deviation from the mean for each data point. For each student, we subtract the mean from their hours studied. This shows us how much each value deviates from the mean. Step 3. Square each deviation. We then square each of these deviations to eliminate negative values. Squaring ensures that all deviations are positive and emphasizes larger deviations. Step 4. Sum up the squared deviations. Adding these squared deviations gives us a total of 10. This sum represents the total squared deviation from the mean. Step 5. Calculate the variance. Variance, denoted as S2, is found by dividing the sum of squared deviations by the number of data points minus 1. This gives us an average squared deviation. So 10 divided by 4 equals 2.5. This is our variance, which measures the spread of our data set. Step 6. Calculate the standard deviation. Finally, the standard deviation, denoted as S, is the square root of the variance. This step brings our measure back to the original units of the data. The square root of 2.5 is approximately 1.58 hours. This is our standard deviation. Therefore, the standard deviation of the number of hours studied is approximately 1.58 hours. This value gives us an idea of how much the study times vary from the mean. This tells us that, on average, the individual study times of these students deviated from the mean study time of 6 hours by about 1.58 hours. Understanding this helps us grasp the consistency of the data. Section 6. Interpreting standard deviation. Understanding what standard deviation represents is only half the battle. It's crucial to grasp how it applies to real-world scenarios and data sets. The other half is interpreting its significance in context. This means looking at the data and understanding what the standard deviation tells us about the variability and reliability of the data. Generally, a low standard deviation indicates that the data points are clustered closely around the mean, suggesting that the mean is a good representation of the typical value. This can be particularly useful in fields like quality control and finance. On the other hand, a high standard deviation indicates that the data points are more spread out, suggesting that the mean might not be the best representation of the typical value and that there is more variability within the data. This can signal potential issues or the need for further investigation. In our previous example, a standard deviation of 1.58 hours is relatively low, suggesting that the students' study times were relatively similar. This consistency can be important for planning and resource allocation. However, the interpretation of standard deviation can also depend on the scale of the data. Different contexts can change what is considered a high or low standard deviation. For instance, a standard deviation of 1.58 hours would be considered high for the daily sleep times of adults, which typically fall within a narrower range. This highlights the importance of context when interpreting standard deviation. Section 7. The importance of standard deviation in research. Standard deviation plays a crucial role in research across various fields. Here are some key reasons why. Estimating the accuracy of measurements. In scientific experiments, standard deviation helps assess the precision and reliability of measurements. Comparing groups. Researchers often use standard deviation to compare the variability between different groups. For example, a study might investigate whether a new drug leads to greater variability in patient outcomes compared to a standard treatment. Determining statistical significance. Standard deviation is a key component of many statistical tests, such as t-tests and ANOVA, which are used to determine whether observed differences between groups are statistically significant or due to chance. By understanding standard deviation, researchers can gain deeper insights into their data and draw more meaningful conclusions from their findings. Section 8. Common misinterpretations of standard deviation. While standard deviation is a valuable statistical tool, it's important to be aware of common misinterpretations. Confusing standard deviation with standard error. Standard deviation measures the variability of individual data points around the mean, while standard error measures the variability of the sample mean itself. Assuming a normal distribution. Standard deviation is most meaningful when the data follows a normal distribution or bell-shaped curve. However, not all data sets follow a normal distribution, and in such cases, alternative measures of variability might be more appropriate, ignoring the context. As mentioned earlier, the interpretation of standard deviation should always consider the context of the data, including the scale of measurement and the specific research question being investigated. Avoiding these misinterpretations ensures that we use standard deviation appropriately and draw accurate conclusions from our data. Section 9. Conclusion. Embracing the power of standard deviation. Standard deviation is a fundamental concept in statistics that helps us understand the variability within a dataset. By quantifying the average distance of data points from the mean, standard deviation provides valuable insights into the distribution of data and plays a crucial role in various statistical analyses. From interpreting research findings to making informed decisions in our daily lives, understanding standard deviation empowers us to navigate a world awash in data. By embracing the power of standard deviation and other statistical tools, we can move beyond simply collecting data to actually understanding the stories it tells.